Hi, everybody. Today, I'm going to be talking about taking care of the bits and letting the gigabytes take care of themselves. What do I mean by that? Well, this is going to be a talk about memory efficiency in in-memory databases and how you can use that to take what you already have and then store more or even take down some infrastructure. So, why should you listen to me? Well, my name is Kyle, and I have been using in-memory databases since around the end of 2011. Back then, I was working on a specific uh, application that required a lot of performance and a very tight performance envelope. And in that application, I originally used a relational database, used disk-based storage, and I saw that my bottleneck was really that database. It was kind of slow. And then when I started profiling memory on just running that database, it took hundreds of megabytes of RAM up, and this application that I was building required a very small amount of actual data. And I said, I could just store this in memory. And so I made the next logical choice was I'm going to build my own database, which is never a good idea when that's not what you're trying to set out to do. So I quickly found out that that was kind of nuts. And so I decided that I would seek out something else. And I found this database called Redis. And it solved a lot of my problems. So that was around 2012 is when I actually started using Redis, early 2012. And when I started using it, I changed everything and I found out all these neat tips and tricks and really how somebody can use this to really do a lot of different things. So I started writing about it and sharing that. And a little bit later, a company called Redis Labs decided to hire me because of that writing. I worked there for a long time. And then I went to AWS and started a few open source projects. One of those is the Valkey project, we'll get into later. But now I don't work at AWS, I work at Percona. What is Percona? Well, Percona is, it's hard to describe, but the way I like to describe it is basically a big collection of like kind of database geeks and open source geeks that kind of work to help you run your database and support your database. So kind of you can have kind of an extended team almost. Um, we have a lot of different things we offer. But one of our specialties is Valkey and Redis, as far as products are concerned, and that's actually my job. I am the general manager of the Redis and Valkey ecosystem at Percona. So what does that mean? Well, my job is to manage all that we deliver for Redis and Valkey, whether that's contributing to those projects or to projects around those. That might be supporting our customers, um, you know, uh, all the different things from beginning to end on that. So I've only been here for a little while, a little over a month, so it's a relatively new role to me. Um, Before we get further, I do want to talk a little bit about how this all came about. I maybe mentioned some things vaguely, but let's look at the whole history and why we can talk about these things in a very broad stroke and why we're talking about two different products. So in the beginning, there was Redis, and that started around 2009 as a open source project created by a guy named Salvatore Sanfilippo. He didn't go out to start a company based on it. It was kind of a sideline. It was an open source project. Um, and he worked on it a number of years. Various companies sponsored him. And then a company called Redis Labs, which I mentioned, I worked at as well. They started offering it commercially. They were a different name initially. And then they hired Salvatore. So Redis Labs wasn't the kind of originator of the project. It's kind of the TLDR there. Um, a little bit later, they hired me, and there was a dust up, I think around 2019, where some of the extensions were not open source. They were in a source available license, and the community really didn't like that. Um, and there was a blog post that went out that said Redis will always be open source or something along those lines. Um, Salvatore left. Since he was the benevolent dictator for life, BDFL, of Redis, they replaced that singular role with a kind of community governance made of people from various different companies, AWS being one of them, Alibaba being another one. There's some other ones that eventually kind of evolved in that. And so from the kind of like 2020-ish timeframe, That's how it was run. And there was, of course, people from Redis Labs on that community governance piece. Everything was working out pretty good. And then in 2024, March of 2024, I believe, kind of suddenly, the company that was Redis Labs, they changed their name a little bit, decided that they weren't going to have open source Redis anymore. So they changed the license to a proprietary license. Those folks that were on the community governance all said, we're not part of that governance anymore. They weren't invited to be part of it. So they forked it. And that fork is Valkey. And that was under the original license. So from 7.2.4 Redis, which is the last BSD licensed version, that was formed. And so for a while, there was no open source Redis at all. And Valkey was being developed. Meanwhile, 18 months later, I think, something along those lines, a little while later, less than that actually, Redis came along and they said, guess what? We're going to add another open source license in. So it had the two proprietary licenses it was released under originally in that period where it was non-open source Redis. And from there was the AGPL licensed version. So the licenses themselves are not particularly important, but how they kind of play into it is. So right now we have two different products that are out there, two different projects, Valkey and Redis, and they share an API. So the API is for each of those is a superset of Redis 7.2.4's API. So that API has been largely stabilized for like a decade. Most applications you're going to run into use the kind of pre-7.2.4 API, but both Valkey and Redis have developed kind of independently over the intervening time. And so when we take a look at this, we can see that they will change and evolve. There are some common things that have developed between them. The other important thing to know is that a lot of the changes that have happened have been kind of internal changes. The APIs haven't changed that much, but internally they're starting to be very different. Some of the internal changes that Valkey made were adopted by Redis. They can do that because BSD is a more permissive license than AGPL, but we can't go the other direction. So Redis does not adopt, or Valkey does not adopt Redis commits, if that makes sense. So in this talk, I'm going to go and talk about the internal changes in just a moment and why that's good for the framing and understanding what's going on here. And then we're going to take a look at a number of changes that you can apply to both Redis and Valkey. So looking at that, let's go ahead and take a look at a few blog posts from the Valkey ecosystem. So if we look here, I want to start with kind of three important blogs that have a similar theme. This was part of the release process of Valkey 8 and happened in September 2024. This is the first major version of Valkey. So what's important here is this is by my friend Hari at AWS. He does quite a bit of work on Valkey. Here it's talking about rewriting some core components of how keys are stored in Valkey. This is a good read. You should read it. But it came out with two key optimizations: a dictionary per slot. Slot is kind of the fundamental thing that we use in clusters to divide up the keys. It's not super important to understand that. But what is important to understand is the optimizations that came from this. So this optimization added or got rid of 2 pointers, which means that that's 16 bytes of RAM per key. Doesn't sound like a whole lot, but stay with me. The second optimization is how the keys are embedded directly into the dictionary instead of being pointed to another part. That added an additional 8 bytes. So now we're up to 24 bytes per key. Now, if you have 2 dozen keys, this does not matter at all. But when you get into millions and millions of keys, which is a typical workload for Valkey or Redis, this starts to add up in a big way. So let's fast forward to 8.1, which was in March of 2025, a little over a year ago from when I'm recording this. This is a blog post by Victor Soderquist from Ericsson, who's one of the TSC members of Valkey. And he's talking about how, again, the dictionary works, right? How it works now, and then how some optimizations that they're doing. Again, I'm not going to reread this to you, but I do want to highlight a couple things in it. When we see this, there's a big reduction. So by replacing the hash table with different implementation, we managed to reduce the memory usage by roughly 20 bytes per key. Again, this is actually adding up from what we saw in Valkey 8. So 24 plus 20, 44 bytes per key. That's actually a lot, especially with millions of keys. I'll provide where you can read these later, so don't worry about that. Now, let's go in and talk about numbered databases. This is a little different. It's a blog post I wrote as part of the release process for Valkey 9.0, and this was in September 2025. Numbered databases are a pretty simple concept. They're effectively a namespacing system in Redis and Valkey. It has existed for a very long time in both of them. Redis originated as a single instance that could not be scaled out. It was basically, lived on one machine and that's it. They came out with the cluster spec and they did not include numbered databases for a variety of reasons. However, this has still remained to be a very popular thing to do with Redis or Valkey. People would do this on a single instance and then they would get to the cluster mode and realize they can't move. Valkey 9 brought this to cluster mode. So that's the story here. Where does this come into memory efficiency? So if you really start thinking about it, the convention in Redis and Valkey is to use part of the key as a namespacing mechanism. So your key might be, players in a game, PLAYERS colon, and then all of them begin with that. Maybe you have an ID after that. And then you might have other things too, like in a game, you might have enemies, right? You have enemies colon. So you are identifying these things so you don't end up with clashes. Numbered databases in Valkey 9 allow you to have the same key name and representing two different values. And you can address them by numbers. So effectively, database 0 with key foo can represent one value. Database 1 with key foo can represent a different value. Not terribly complicated. Memory efficiency. How does this come in? Well, again, if we're talking about things that happen on every single key, and we're using part of that key as namespacing and we're putting characters in there, those namespacing pieces actually end up adding to a lot of space. So if you think about it, you have players, you have millions of players, that is repeated every single time. So when you start thinking about this, there's one line here that I wrote. The prefixes, that's what they call this, prefixes add up at scale. And those millions of keys require you to repeat this over and over again. So if you say, all my players go in one database and all my enemies go in another database, you can eliminate those from the key space entirely. Again, that's saving 5, 6, 7, 8 bytes per key, but you're not really losing anything, right? This is an application level change. The other two are just internal changes that you need to make. But it's a really interesting pattern. You can constantly save things over a small scale. So with that concept in your head that we're going to save little bits over a small amounts of memory over a lot of different items, let's take a look at how we can do that from an example in my presentation. So I want to scale out here. Okay, this is a hash map or representation of a hash map, I should say. And Valkey and Redis, you have different data types. A hash map basically is a key that contains fields and values. And this representation on the left side is all of our fields. So username, background, so on and so forth. And their corresponding values are on the right side. And we're representing what's called a session store. And I'll explain a session store just a little bit. A session store is effectively a way of storing a little bit of data in one centralized location for users. So in this example, you might have an application that has many application servers behind a load balancer. A user hits the first time and they get load balanced to server 1, for example. And if there's anything that you need to persist in those sessions, so between page views or instances of access or whatever, then you can't store on that machine. You have to store it in a centralized place. This is a really common use case for Redis and Valkey. So you would have one of these per every user that's online. A lot of times you keep them around, so logging in is quite easy, stuff like that. So when they're redirected to another one, you can still retain that data. And this is actually something that I saw in my own life. So I was poking around on my own bank account of all things. This is, of course, anonymized. And I started noticing that they were carrying a lot of these things and coming across and then being registered as cookies. This is not always the case, but most of the times that's kind of what's in your session store. And we see some of the data that look like this. And I said, wow, that's really interesting. And let's talk about why. Now, the first thing we're talking about, this is the database session. So we're going to talk about little Bobby tables. If you know that joke from XKCD, then you'll get it. But we can't do anything with that. Usernames are pretty much just what they are. Um, but we start getting interesting when we get into the next two, background and foreground. Contextually, we look at this and we say background and foreground, and then we see hexadecimal representation, 6 digits long. That probably represents a 24-bit color space where we're just having, a few bytes basically of information, 250, 0 to 255 for each RGB value, right? So that would be effectively 3 bytes for each one of these. Now, we're writing it in hexadecimal. What if we wrote it in binary? If we wrote this in binary, then of course, 24 bits would be, 3 bytes. And instead of 6 bytes in this representation. So we're saving 50% right there. But that's just 6 bytes total, not a whole lot. Let's take a look as we go down. As I mentioned before, this is something that I noticed in my own life, just kind of casually, and I go, oh, something interesting is here. Do you know what these are? I'll give you a few seconds. These are UUIDs. UIDs are basically hexadecimal representations of 128 bits. And they have dashes in certain spaces in different sequences in this to represent what type of UID it is. That particular part isn't that important, but they always represent 128 bits. So if we look at this, that's a lot more than 128 bits because it's written hexadecimal with these dashes in it. So we could potentially represent this in binary as well. Next up, we have our series of flags, effectively, Booleans, and they're true and false. Now, obviously, a Boolean can be represented by a single bit. Maybe we can't represent it as a single bit here. It's certainly represented as a single byte because true, True, for characters, but we could also represent it as a 0 or 1 and really retain kind of the same value. And finally, at the bottom, we have a date. It's written out in longhand that's human readable with a year, month, day format, but we can also represent this in binary as well, using kind of like a Unix timestamp or something even smaller than that. So I started thinking about this and I was like, there's just a lot of waste here, right? And because this is something that happens to every single user, you could potentially have millions and millions of these. So, and I would say actually this is a relatively small session store element. You probably will have them much larger. So, but just for argument's sake, let's take a look at what we can do if we look at the size of this. Now, in Redis and Valkey, there is this idea of a memory usage. This goes and says that this key, which we see the name of the key here, has 1,328 bytes. So, can we do any better? I think we can. So I've taken here and represented the binary by its representation. The weakness of binary is that despite Redis and Valkey being binary safe, not very good to look at. We can get all sorts of characters, maybe even unreadable characters that make it not very useful, but we're not looking at this with human eyes. Redis and Valkey are kind of a developer database. We're always hooking applications up to it. So we can represent it as binary just as easily. You can see these are much shorter, right? Look at just with your own eyes, you see that this is just much less. And we see our Booleans represented by 1 value, and we're using just a handful of bytes here, right? So this makes a lot of sense. Just by doing this kind of single optimization, what can we expect? Here, I'm going to show you. Now, this is 816 bytes. It's the same information. We're just representing various fields in different ways. And if we take a look at it, this is 61% of the original size. So you're already saving a bunch by just making this small change. But can we do better? I think we can, and I think substantially. Now, the one thing that you might think about looking at this is it looks kind of like a row in a table if you're used to relational databases, but it's actually incredibly different. The reason it's incredibly different is that the fields are stored on every single key. They are effectively independent. They could be different ones every single time. So we start thinking about the left side of this little chart here, or this table. We can see that we're saying statement over and over and again a lot. And we're not adding a lot of value. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So can we represent this in a different way that uses less fields? And I think we can. So let's go over here. We'll do a small change here. Instead of sequentially representing these, we're just going to combine them into a single field. So each of the bytes is, we have these certain number of bytes. We can go and pull these out by 128 bits at a time. Actually, really easy to do. One-liner kind of just like this, pulling out like the third statement. And something you can even do in JavaScript. Actually, really simple to do. So once we've done that, we would expect it to be a lot smaller because we've taken statement out many, many times and the overhead for the fields and values are gone. Let's take a look at the size of this key now. Something has gone wrong. We are now looking at a situation where we went from 816 bytes and we moved up. Why is that? We can see we're even larger than our last one and a little smaller than the original, but we're still larger. We've really lost something. Well, what I'm going to tell you to do is look at the object encoding. So I look at this, the object encoding of this. There's this idea of an object encoding. So let me back up a little bit. Object encodings are how internally data is represented in Redis and Valkey. Now, I'm using a hash data type. One would expect that the object encoding would be hash map as well. But that's not always correct. So let's look at the object encoding of other ones, right? The other keys in this example. Go over here. This is a list pack, and so is this. What is a list pack? Well, a list pack is a different encoding that Redis and Valkey uses that's more compact when in memory representation. And for a smaller number of fields and smaller values, the CPU advantage in having a true hash map versus list pack is negligible. So it's automatically kind of doing this encoding change for you. But we're trying to make as much fit into the space as possible. So let's see what I can do. Now, why is it doing it is the first thing you should think about. I know that there is a configuration for this. If I look at this, the configuration is config get. That'll get a configuration generally, but the configuration line itself is hash max list pack value. And that will return that particular value. And it's 64 bytes. So once any field in a hash map, or hash data type, I should say, gets above 64 bytes, it's going to transition that particular hash map or hash data type to a hash map from a list pack. So can we avoid this? Well, obviously, since it's a configuration, if we set the configuration, we can then change it again. So here, I'm looking at it, and we have 193. So we've upped it, we've set that. And then when we take a look, I'm going to do what's called a dump restore. This will give you a serialized version of the data, and then you will actually take that and just restore it under a different field name. And this will reset any of our expectations that are set by the original configuration value and the encoding. We have the same exact value. Same value. But if we take a look at the memory on this, I think we're going to be very pleasantly surprised. Here we go. Our memory now is 576 bytes. We can see our original was 1,328. So our size is now 43% of the original size. Incredible savings by changing configuration and changing some representation in it. Now, there may be some losses when it comes to, are we hitting multiple cache lines, which is possible, but we're gaining a lot. And what are we gaining, right? When I start looking at this, I want to look at what a generalized cluster looks like. So we have a cluster here, and this is just an example. It's very simplified. The numbers are rounded over, that sort of thing. So we have 5 primaries in this cluster, and then 2 replicas each of the 5 primaries. So we can see of the 5 primaries, we get 100 gigabytes, we have 20 gigabytes each. And then if we start thinking about that, we're holding 100 and 43% of the original size, we can cut out just a lot of the infrastructure here. We don't need this. We don't need the overhead of handling it. We don't need anything here. And we're just already good. And we actually have quite a bit. We're limiting 6 to 15 machines in this example. We even have some extra overhead too. So the total under management is 60 if we're using the same infrastructure. Now, if I look at this cluster and I see that we only have 20 gigabytes per primary, that tells me we're probably trying to optimize for performance as well, higher throughputs. You will see a slight increase in throughput because we are just transmitting less data back and forth and storing less data. So it's just less to do. I don't know if it'll balance out always, but let's talk about maybe what other things we can do with it, kind of maintaining our throughput. And it becomes very interesting. Second scenario, I'm going to say that we're going to take and we're going to have some of the cluster storing one type of data and another part of the cluster storing another type of data. Obviously, in this case, we're not specifically actually holding things in individual like parts of the cluster. It's just for visual representation. But if you can visualize this, the green stuff is their existing session store, and then the purple stuff is things that we now can cache that we could not cache with that. And if you're using those kind of numbered databases, that makes it really easy to divide up things and not have any clashes with keys. So the scenario 3 is where we're still just using everything, right? When we use everything, we're just kind of keeping headspace, right? And that's going to yield some really important properties here. We can have less eviction, and in Redis and Valkey, you can set up an eviction. So when the memory gets full, it's going to evict a certain amount of data to make room for new data. We can eliminate having to do that very often if we have more headspace. So we're storing, like, where basic utilization is much lower. We can have maybe longer TTLs, time to live. So our keys stay around a little bit longer. There's less kind of thrashing, load on other data stores. And this will just be kind of faster overall, given what we're trying to do here. This will kind of increase your general performance because your application is doing less for the same amount. So really big savings there. But if it's me, I might want to take this option 1 where I'm removing things entirely. So what's the TLDR of this presentation? Small changes add up at scale. When you make a small change over many, many things, you can actually get to some real magic here. Choose binary whenever possible. People overlook the property of Redis and Valkey being binary safe all the time. You can make everything. You can make your keys binary if you want to, much less common. But from the keys and values, you are making some exchange for like the CPU to re-encode those to whatever thing you need, but that can be done even on client side. It's a really simple operation, kind of a single liner thing. Find ways to reduce the number of field names that you have. So you can make them smaller or just eliminate them entirely. In hash maps particularly, you're going to be better off. Pay attention to your encodings. You'll see this kind of like, hump as things get larger. It's often from the encoding being the fast encoding to the slower encoding that occurs that's in the decision, and make those configuration changes intelligently. And space savings can be either thought of as reductions or additions. In the scenarios that I gave you before, those reductions could really be something that you would add more to your ability to cache, or you can just turn off infrastructure. So lots of savings there. Now, what's next? What can you do? If you want to find out more, talk to us about this. Of course, you can go to percona.com/Valkey-Redis. The blog posts that I featured, they're all on valkey.io. And I'd love for you to follow me on LinkedIn. So that's it. Thanks, everybody. Enjoy the conference.